Okay, everybody, let's get started for today. So last time we were looking at our analysis of the common emitter amplifier with an emitter degeneration resistor, and we did the RN calculation, the input resistance calculation. And we got this result. RN is equal to R pi plus beta plus 1 times RE. That beta plus 1 multiplication for RE is due to the current that's being injected into this node by that dependent current source. So I can always tell the people who did not remember Thevenin's theorem by seeing the people who tell me that RN is equal to R pi plus RE and they ignore that dependent source. You can't ignore a dependent source. If there's a dependent source in the circuit, Thevenin's theorem, you've got to use the source driving technique. And in that case, that's what we did with the equations, and we got this result. Now notice, once again, does my answer make sense? Let's do a sanity check. If RE goes to 0, what does this become? Then Rn is equal to R pi, which of course was exactly the result we had with the standard CE common emitter amplifier. So in this case, this is just a quick way of checking. Does my math make sense? If I actually get rid of this extra resistor, do I go back to the equation I thought I had before, or I know I derived before? So it's always a good way to kind of go through and sort of do that, do that sanity check just to make sure your answer does make sense. The units do balance. Okay? Now, what about the output resistance of the amplifier with the emitter resistor? So now we're going to do RO. Well, if we're going to do RO, in this case, I'm going to put back the signal resistance, R sig, but I'm going to zero out V sig. So the V sig goes to 0. So this just becomes ground. And now I'm going to inject an AC current of 1 amp at the output node. And so in this case, this is VO, this is VE, this is VB. So in this case, if I want to solve for this, let's first go through. I'm going to write an equation here. I know that in this case, this current and this current, I'm just going to write a KCL for that node. So here at the base node, what I'm going to have is that 0 minus VB over R sig is equal to VB minus VE over R pi. So that's my base node. For my emitter node, VB minus VE over R pi plus GM VB minus VE is equal to, in this case, VE over RE. Now I'm going to kind of stop right here. I could also write the equation for the collector node because I'm going to use source driving, but as we're going to see, that's not really the case. If we just focus on those two equations there, if we solve for these two, what we find is VB is equal to 0 and VE is equal to 0. So solving for those two equations gives us a rather interesting result, that both of those small signal voltages are just 0. And if that's the case, if VB and VE are both equal to 0, then that dependent current source is equal to 0. So in this case, RO is a trivial result. Of course, I could write the KCL equation using source driving, but really, clearly the output resistance is simply going to be equal to RC. So we get the same result. Interestingly enough, adding the emitter resistor, the emitter degeneration resistor, doesn't change the output resistance of the amplifier as opposed to a standard common emitter amplifier. So kind of interesting result. Incidentally, we'll see this idea of small signal voltages actually being equal to 0, even though it's not kind of obvious by inspection. We'll see this again when we later on get to a differential amplifier, and we'll see this kind of behavior again. All right, so common emitter amplifier with and without the emitter resistor. What changes significantly here? Well, obviously the gain goes down, as we've already talked about, but also the input resistance goes up. However, the output resistance stays pretty much the same, doesn't change. So now let's look at the common base amplifier. So for the common base amplifier, just as it's well with the common gate amplifier, the biasing arrangement is the same, except now we're taking the signal source and now we're moving it and putting it into the emitter instead of into the base. And so once again, we can now go through and do the small signal diagram. And we, of course, want to try to find the gain. And in addition, we want to know what's RO and what's Rn for this amplifier, given the input and output. So in this case, we'll draw the small signal diagram. And we note that once again, we're going to ignore the little r sub o, the collector emitter resistance, because we're going to assume it's large. So GM times VBE, so I'm just decomposing that into VB and VE. Here's VB. Here's VE. And now I can go through. Obviously, VB is equal to 0, so this must be equal to GM times minus VE. And now I can go through and do what I've done before, write some KCL equations and do some algebra. And so in this case, the KCL equations are pretty straightforward here. So in this case, I've got V sig, got this current, I've got this current, and I've got that current. So at the emitter, I've got GM times minus VE plus V sig minus VE over R sig. Must be equal to, these two currents going in must be equal to VE over R pi going out. Since VB, of course, is just 0, right? So I don't care about that. And also I can write the KCL equation at the output node. And in this case, at the collector, VO over RC plus GM times minus VE is equal to 0. And now, once again, I can take those two equations, I can combine them and do some algebra. I'm going to skip those steps. It's just a lot of unnecessary math in terms of the lecture time, but you guys can do this yourselves. But if you do some algebra, what we get is that VO over V sig is equal to GM times R pi times RC divided by R pi plus R sig plus GM R pi times R sig. So a bit of a messy expression, but we can simplify it a bit. So in this case, we know that R pi is equal to beta over GM, and so we can do a little substitution here. And this will be equal to beta times RC divided by R pi plus R sig times 1 plus beta. Now we note, if R sig is small, so if R sig becomes tiny, then in this case what we're going to get is this term and this term go to 0, and I wind up with GM R pi RC over R pi. And therefore the gain becomes this. VO over V sig will be approximately equal to GM times RC. And what do we have here? Common base amplifier has the same gain magnitude as the common emitter amplifier, but now it's a non-inverting instead of an inverting amplifier. No surprise there. We saw that before with the common source versus common gate. Same thing. Same gain magnitude. It's just that we don't have the minus sign in front of it anymore. No surprise there. Okay, what about my Rn calculation? I want to do the input resistance. So in this case, I'd take this small signal diagram. I'd remove the signal source, and I would inject a 1 amp source here into the emitter node and do my Rn calculation. And if we do this calculation, actually if we do this, we already did this. Remember when we did the little R sub E, when we looked at the input resistance seen looking into the emitter of the transistor? We actually already have done this exact circuit, or this exact small signal analysis. And so here, if we want to find Rn, what we will show, or we can easily show, we've already shown for that matter, Rn will be equal to little r sub e. So the input resistance of the amplifier is the input resistance seen looking into the emitter of that transistor, which is little re, which is equal to alpha over G sub m. So look back in your notes. We already did that when we did the little r sub e derivation. No point in repeating it. What about the output resistance? Okay, so with the output resistance, if I want to look at R sub O, and I want to calculate R sub O, in that case I will put back my input source, but I'm going to zero out my VSIG. And then I will use the source driving technique here at the output. But again, let's stop for a moment. Haven't we already done that small signal diagram? Yeah, we just did it. I called it RE instead of RSIG, but it had the same topology. This is the output resistance of the common emitter amplifier with R sub E. So for R sub O, same analysis as the common emitter amplifier plus the emitter resistor. And therefore what we get is that R sub O will be equal to R sub C. So you see a lot of these different analyses start looking very much like each other. Once you see one, you begin to see, oh, it's the same topology as that other circuit. So questions about this? And once again, guys, on the exam, I'm not going to expect you to do this stuff symbolically. Okay, I'm doing it symbolically so you can see how the equations work out. On the exam, my only expectation is that you guys can take numerical equations and then write these equations correctly and solve. Because I'm going to ask for numerical answers. All right, so just to give you a little bit of heads up. All right, you can actually use Mathematica to do algebra, but it can get messy. So here, this is just so you guys can see how the equations work and to see the similarities in terms of how these amplifiers and the differences of these amplifier topologies. So questions about the common base? All right, then let's very quickly close things out by looking at the common collector. All right. So in this case, I've now got my VSIG and RSIG moved back to the base. Now I'm taking my output here at the emitter. I'm taking the collector, connecting it directly to VCC. And once again, let's do the small signal analysis. Rn. Now, incidentally, here's something that a couple of people asked me about that was in the book, and it has something to do with the lecture I did last time. Where's R sub O in a circuit like this? Is that R sub O, or should this be R sub O? Should I or should I not include the load resistor in my calculation? Well, you can argue that either way. Okay? Let me put it this way. If I take the load resistor out and remove the load, does that circuit work? How does the collector current flow? People are nodding heads. Of course it works. What do you mean it works? There's no collector current flowing through the amplifier. It's not going to work. The amplifier, the transistor is off. It's disconnected. So if I remove the load resistor, it's off. So I would argue that the load resistor is a necessary part of the amplifier structure. Therefore, the output resistance should include it. On the other hand, I could say, yeah, but the load resistor can change. It's a load, all right? In that case, I'll look at the output resistance and I'll define it looking at here. So what's the difference between these two values? I'm going to call this, say, RO prime and call that RO double prime. What's the difference between those two? Well, RO double prime will just be equal to RO prime in parallel with RL. So whatever I calculate, I can just add the RL in parallel and get that other load resistor if I want to. So I point this out because when you look at these topologies, different books will define them differently. But I want to assure you that on the exam, I'll be very explicit about where you should be defining RO and R out. I'll make it very explicit on the diagram. If you have any questions, ask me, okay? Because keep in mind, these definitions don't concern me half as much as you being able to show you can use the techniques to derive this. So I just want to kind of throw this out, okay? So in this case, I'm going to do things slightly differently as I did with the common source, because in this case, I'm going to do it the way the book is doing it. I'll define RO looking back into the emitter. And so in this case, I'm first going to go through and do my small signal diagram. Now in this case, I'm just leaving the little R sub O there. There's no reason why I can't do that since it doesn't really make the math any more complex. So I'm going to leave it in here. Here's VB. Here's VO. Here's VE. And clearly VO and VE are the same voltage, obviously. Here's R pi. And I've got GM times VBE, which will be equal to GM times VB minus VE. So once again, I'm decomposing that voltage. And so in this case, again, just doing what we've done before. Here's our base node. Here's our emitter node. Now I can go through and write some equations. And writing my KCL equations, what I'm going to get for my base, that V sig minus VB over R sig is equal to VB minus VE over R pi. For my emitter, VB minus VE over R pi. Plus GM VB minus VE is equal to VE over RL plus VE over RO. And of course, VO is equal to VE, so I can just go in and substitute VO in place of VE in all those equations. So I take those three equations, again, combine them and go through a lot of algebra that I'm not going to spend time on. But if we do that, we will get the following. We get 1 plus GMR pi over 1 plus GMR pi plus 1 over RL plus 1 over RO multiplied times R sig plus R pi. So, yes?
In that equation, should it be VE over RO?
VE over RO. Did I? Oh, I'm sorry. Thank you very much. It should be VE over RO. Thank you very much. Math error there. Thank you. VE over RO. Correct. Okay, so solving those equations, I get the following. What do we note about the gain magnitude from that equation, regardless of the values? What do I know must be true? It's got to be less than 1, right? 1 plus GMR pi is certainly going to be less than 1 plus GMR pi plus the additional terms in the denominator. And so clearly, V over V sig must be less than 1. If we can make RL larger, and if we can make little r sub o larger, then V over V sig will approach unity. But we'll never quite get there, because of course we can't get infinite values. But if we increase them, make them bigger, the gain will approach unity. All right? So, no surprise here. We saw something very similar. Okay, a little bit. So this is a little more messy, but we saw something very similar with the common drain amplifier. It's a unity gain buffer amplifier. What about the input and output resistance? Well, let's see here. So if we look at our Rn for our amplifier, let's go back up here real quickly. So in this case, I'm just going to remove the source, do a 1 amp into the input, do source driving into the base so that I can derive my Rn value. And now I'm going to calculate my input resistance, but hold on. Do I need to write equations for this? Didn't we see this problem before? Very similar topology just a minute ago. Yeah. This looks like the same common emitter amplifier with an RE analysis we just did earlier, isn't it? All right. So for Rn, that's very, very similar to that. So the only difference is I've got RL instead of RE, and I'm including that little r sub o. But other than that, it's the same. And we can easily show this is true, that this is true. That Rn is equal to R pi plus beta plus 1 times the resistance at the emitter, which instead of being Re before is now RL in parallel with a little r sub o. So same problem, no point in repeating it. What about RO? Well, for RO, I'm going to go up to this problem. I'll replace my input. And in this case, I'll put my R sig back. Set V sig equal to 0. And in this case, I'm going to remove R sub L because I'm going to assume that RO is looking directly into the emitter. So I will put my R sub O here, or my 1 amp source here, I'm sorry. So I'll put my 1 amp source and inject it into here in order to calculate R sub O. And again, haven't we seen this? Yeah, we did this for the common base circuit, for the input resistance for the common base, which also happened to be just like the little R sub E calculation, all right? Except it's a little more complex now because we've got this additional resistance here, the R sig. So the resistance terms are a bit different. But what we get is this. So this is very similar to our common base RN analysis. And again, I'm not going to bother to write equations, but again, we can show the following. We get this kind of messy equation because of the extra resistors we have in the small signal diagram. But if we make an assumption, if this term, if R pi plus R sig divided by little r sub O is much, much less than beta, which is probably a good assumption because r sub O is going to be a big number. And so beta is probably going to be much bigger than the 1 or this term here, than what we're going to get. Then r sub O will be equal to r sub pi plus r sig divided by beta plus 1. And if r sig is also small, then what we get is that r sub O will be equal to r pi over beta plus 1, which will be equal to alpha over g sub m, which will be equal to little r sub e. Hey, no surprise. I would expect to see that, right? I'm looking up into the emitter of the bipolar transistor. And so with a little bit of extra resistance in parallel due to those extra terms, which I assume are going to be large compared to the little r sub e, I get this result. And of course, r sub e, as we already know, since alpha approaches unity, then r sub e is going to be approximately 1 over gm. So you look up into the source of a MOSFET, you see 1 over gm. You look into the emitter of a BJT, you see 1 over gm approximately. Now, what if, just to add this, what if I had included that load resistor and I had defined r sub O, I'll call it r sub O prime, here. I defined r sub O prime that way. What am I going to get? Well, in this case, r sub O prime must be r sub O, whatever that is, in parallel with r sub O. Okay, so we note that r sub O prime is equal to just RO in parallel with RL. which, since R sub B is probably much smaller than R sub L, will still be approximately equal to R sub B. So again, it all depends upon where the book or the problem defines your output resistance, whether it wants to include or not include that load resistor. But regardless, the dominant resistance is still going to be that 1 over GM, because that's going to be the smallest resistance when you go ahead and do the math. Okay, now you guys, you notice what I'm doing here? I'm just doing literally nothing but writing the KCL equations and solving. 2112, right? I'm just not bothering to go through the drudge of doing the algebra, but this is all stuff you guys can do. Yeah?
Why did we include little r sub O here but not the others?
Because it was easy to include, okay? Before, it was mathematically messy because it was connected between the collector and the emitter, and neither one of those was grounded. In this case, because the collector is grounded, R sub O, we might as well just leave it in there, because it just then becomes a resistance in parallel with R sub L or with the other resistors connected at the output. So for no other reason than that. But again, that R sub O is going to be big, okay? So this term just drops out anyway, and it really doesn't have any effect. But yeah, that's the only reason I included it. It was just mathematically easy.
So you can still assume and leave it out as long as you still.
Oh yeah, exactly. You could still drop the R sub O out completely. If you took the R sub O out of this equation, it would have almost negligible effect on your answers, on your results. Now, on the exam, for example, okay, sometimes I will tell you, assume that VA is very, very large. So I'm just telling you R sub O is small. Or you can make the assumption. You can say, hey, R sub O, I'm going to assume R sub O is really big compared to these other resistors. So if your other resistors are a few kilo ohms, and you know R sub O is going to be 100K, it's a reasonable thing to assume it's small enough to ignore. So those are always good assumptions. But you should always state your engineering assumptions, just to make them clear. All right? So, questions about any of this? Once again, on an exam, this will all be numerical. So you just have to write the equations. But I wanted to go through this exercise so that when you get an answer, you will know if the answer makes sense. Okay? So, for example, if you calculate the gain of a common emitter amplifier and get a value of 53, there's something wrong with that answer. It should be a minus 53, right? Shouldn't a common emitter amplifier be an inverting amplifier? Yeah, okay. So that's what I want you guys to think about. Think about the general properties that come out of these equations. It's a way of looking at your numerical answer on an exam and looking at that and saying, okay, does that make sense? All right. Dr. Holman asked me to calculate the gain of this common emitter amplifier. The gain is 0.3. Does that make sense? Would Dr. Holman give me an amplifier that doesn't amplify if it's common emitter? Well, if I were really being cruel and I was a terrible professor, yes, I might do that. However, since I'm a good professor, I prefer to give you circuits that work for your problems, okay? So I always say this to everybody. I don't give broken circuits on exam problems, okay? Oh, I'm so clever. You guys couldn't figure out I tricked you. Oh, no, I'm sorry. I don't do that stuff, okay? I'm going to give you circuits that work because believe me, you'll have ample opportunity in your careers to break circuits yourselves. I don't need to do it for you, okay? All right, so questions about this? All right. So to kind of summarize, if we look at these three topologies and kind of pair them together between BJT and between MOSFET, let's consider the magnitude of the gain, R sub n, and R sub O. And what do we see for these? Okay. For a common source, common emitter amplifier, the gain is typically going to be, moderate to high gain is what we normally aim for. And it's going to be and inverting gain. Input resistance will be anywhere from moderate to infinite, of course, if it's a MOSFET for common source. So I'll just say moderate to high, because certainly high, infinity is high, okay? Output resistance also tends to be moderate to high, okay, depending upon the value of the resistor. Common gate, common base, they have a positive moderate to high gain. But the input resistance tends to be low, on the order of 1 over GM. Output resistance is the same as for the common source or common emitter, so that tends to be moderate to high. Common drain, common collector. In this case, the gain magnitude is less than 1. They're unity gain buffers. Input resistance tends to be moderate to high. But output resistance is low, again on the order of 1 over GM. So this is kind of like compares these three types of topologies together and shows you the properties. Now incidentally, what if I needed an amplifier that needed both low input resistance and low output resistance? Does this mean I can't possibly build an amplifier like that? I'll have to, well, put it in a simpler way, I'll need more than one transistor, right? Exactly. And we'll talk about that later. Obviously, if I need something with properties outside of this table, I need more than one amplifier. I need to combine transistors together, build a multi-stage amplifier, for example. And we'll get along into that because, like I said, ultimately before this semester is over, I'll show you guys how to design a simple op amp. And we're going to put all these ideas together. Okay. All right, so now let's move on and start talking about biasing. You know, when I'm going through and I'm drawing these circuits, you guys have seen how I just throw a V bias, a DC, and I would just zero it out when I did these analyses. Well, obviously, in a real circuit, you're not going to go through and put in DC sources at the gates and at the bases of the transistors. You're not going to put in battery voltages of different voltages. You need a different way to bias circuits. So let's talk about some of the aspects of practical biasing. Actually, I'm going to go ahead. Yeah, I'll do it up here. Let's do it here. So here's where we start to get into some reasons behind why we do some of the things I've been showing you guys. So practical biasing techniques. Well, what's one of the most common ways to bias a base or a gate? And let's start with a MOSFET. Let's look at MOSFET biasing. Well, what have we been doing so far in the labs and in the problems I've been showing you guys? We use voltage dividers at the gate in order to set a gate voltage. And so in this case, I'll do a circuit like this. And I'm going to, in this case, I'm just going to do a simple common source amplifier like we've already done. So here's my CS amp. And in this case, I'm going to have resistor R1 and R2. And VG is just going to be set by that voltage divider. What's the current going into the gate of that transistor? 0. Makes it easy. All right. So that's an easy calculation to find VG. Except, in order to make this amplifier work, I need something. I need a way of connecting the source to this circuit. How do I do that? Well, here is where the power of a capacitor comes in. C sub C is a coupling capacitor, and typically we make a coupling capacitor large. We make it big enough so that the impedance approaches 0 for all AC frequencies of interest. So we just assume it's a big one. And typically in the lab we'll use like 10 and 100 microfarad type capacitors. And if you calculate the impedance of those at 1 or 10 kiloohms, you're talking about an ohm, okay, a few ohms at most of magnitude, which is negligible compared to the resistances in the circuit. So the nice thing about this is C sub C blocks DC current. Therefore, adding the input source and the capacitor has no effect on the DC bias. That's the beauty of using the capacitors. We can use that to separate our DC and our AC circuit topologies, make them different. All right, so we've actually been doing this in the lab. You guys have seen this. But you know, there's something else we've been doing too. And we've already done this. I've shown this to you guys. You've seen it in the lab. We've been adding source resistors into here. We've done the derivations of source resistance. You know, why would we do this? Because I've also shown you guys how to bypass the source resistance with another large capacitor so that in the small signal diagram it's not even there. So if we're going to bypass it anyway, why in the world would we even include that source resistor? Why is it there? And yet they're used all the time. Well, there's a very good reason. As it turns out, doing this, connecting the source of the transistor directly to ground can have some undesirable consequences in terms of creating a stable bias point. Let's do some math, see how this works. And as always, the key to understanding is do the math. So in this case, let's take that circuit and let's plug in some values. Let's plug in some numbers. So why do we include R sub S, the source to generation resistor? Let's analyze the circuit without R sub S. So I'm going to plug in some values for the resistors. I'm going to assume I have a 5-volt power supply. And in this case, I'm going to go through and I'll assume that K prime N is equal to, pardon me, I should say K prime N W over L. I'll just combine those together. Let's assume K prime N times W over L bundled together is equal to 2 milliamps per volt squared. So that's the full transconductance parameter, including the W over L. Let's also assume this. V sub t is 1 volt plus or minus 0.2 volts. Now this has everything to do with real-world circuits, because what do we have? We have tolerance in all components, including transistors. So let's assume that this 1 volt is our nominal value. And the plus and minus 2 volts is, in effect, process variation. It's tolerance. Okay, when we're manufacturing this circuit, we're just pulling transistors out of the box and we're sticking them into the circuit board. We're not measuring the individual transistor values, but we know what the tolerance is. And what we're saying here is on the manufacturer's data sheet, what it's saying is this, that VT is going to have a range like this. Probably going to be Gaussian, and it's going to have a value of 1 volt, and say 99% of all the other values will fall within plus and minus 1.2 to 0.8 volts. So this is what this means, okay, when we're going through and looking at this for VT, is you're going to have typically a kind of Gaussian tolerance description, probabilistic description. Every component you will ever purchase will have this. If you want to tighten up that tolerance and make it narrower, what do you have to do? Spend money. It's going to cost you more money, right? If you want tighter tolerances, better tolerances, you have to pay for it. So components with big tolerances are cheap. Components with very tight tolerances are expensive. Because quite often what's happening is the manufacturer isn't necessarily doing this on a different assembly line or manufacturing them on a different manufacturing line. The manufacturer is doing the sort for you. So they go through, they sort them out, and then they measure them all, and they say, okay, all these transistors are within 1%. Those go into the 1% bin. So quite often when you buy a 1% versus a 10% component, they came off the same manufacturing line. They were just sorted for you. So if you want to buy a bunch of 10% components and sort them yourself, you can get the 1% tolerance, but nobody does that. You pay the manufacturer to do that for you. All right, so let's go through and let's find out what happens to the bias point given this tolerance. Okay, how much does the bias point shift? Well, in this case, we can easily show that the transistor is going to be operating in saturation. I'm not going to bother to prove it, but I'm just going to go ahead and calculate the value of ID. So it'll be 2 milliamps per volt squared divided by 2 times VGS. Okay, what is this? It's 2 volts. It's 20K divided by 20 plus 30 times 5. So VG is 2 volts. And then my nominal current is 1 milliamp. Okay, so this is what I designed for. If I look at the data sheet, it says VT nominal is 1 volt. I say, okay, great. I want a 1 milliamp current, except that I don't know that the next transistor that comes out of the box has a VT of 1 volt. All right. if we take the VT variation into account, what happens if the threshold voltage is small? What I will get is ID will be equal to 1 milliamp per volt squared times 2 minus 0.8 squared is equal to 1.44 milliamps. And if VT is equal to 1.2 volts, then ID will be equal to 1 milliamp per volt squared times 2 minus 1.2 squared is equal to 0.64 milliamps. All right. And just to add some numbers for VD, if we were to calculate this, I could also show that VD would be equal to 2.12 volts. And in this case, VD would be equal to 3.72 volts for this transistor. And in this case, and originally it would just be equal, in this case, to 3 volts for my nominal value. Okay. Now in each of these cases I can prove the transistor remains in saturation, but what is interesting about these results? Notice I have a variation of plus 44% and minus 36% from a 20% variation. And why is that? Because it's being squared. And so that makes the effect of the tolerance even worse. All right? Now, if you can live with this amount of variation in your bias point for your design, fine. Go with it. Except that you may have a design where you can't tolerate this kind of variation. And yet, you may also have a supervisor that tells you, we can't afford those more expensive transistors with tighter tolerances. I want you to figure out how to use these cheap, sloppy transistors in order to save us some money. Because after all, what do we pay you for? You're an engineer. All right? Well, you're paid to figure out how to save money, among other things. What do we do? Well, this all comes back to, why do we include R sub S? Let's do this problem again, only now let's add a source resistance to this circuit. So let's add R sub S to our circuit. In order to make this work, we have to make some adjustments to the component values. So let's choose R1, R2, and RS such that we still get a nominal value of ID equal 1 milliamp. So I'm going to pick some values to make that happen. Okay, in order to get 1 milliamp, I have to have 2 volts between for VGS. Okay, we already know that from the ID equation. So we still need VGS equal 2 volts for ID equal 1 milliamp. That doesn't change. The difference now is, here's our VGS. And unfortunately, the source is no longer grounded. So I'm going to allocate a certain amount of voltage drop across that source resistor. I'm just going to let Vs be equal to 1 volt. It's a somewhat arbitrary number. But what I'm doing is I'm going to make this equal to 1 volt. So that lets me set an RS value. And if I've got 2 volts here, that means I've now got 3 volts on the gate. So again, this was a somewhat arbitrary choice, my choice. I could make that number larger or smaller. But the value I choose is going to set the value of R sub S. So in this case, I still want 1 milliamp flowing through that 2K resistor, which incidentally also flows through R sub S, right? So I've got 1 volt divided by 1 milliamp. What does R sub S have to be equal to? 1K, all right? Therefore, and if I want 3 volts, I have to choose R1 and R2 values to give me 3 volts. You know, let's, sometimes I'm a good engineer, but I'm a lazy engineer. I've already got this 30K and 20K resistor. Let's swap them. And that way I'm going to change the voltage divider so it's 30K over 50K. And so in this case, I'm going to let R1 equal 20K and R2 equal 30K. And therefore, VG will be equal to 3 volts. All right, so I've got the values I wanted. That is now my nominal value, my nominal bias point, my nominal drain current. Now, let's now put in different VT values. We're going to put in different transistors on the manufacturing line. Okay? So to solve for this, let's first let VT equal to 0.8 volts. So in this case, these were the nominal values, so I can't make these assumptions anymore. This, of course, is still 3 volts at the gate, but I don't quite know what these voltages are going to be now because the threshold voltages are going to change, okay? So let's see what we get here. VT is equal to 0.8. Vs is equal to RS times ID is equal to 1,000 ID, which is the value we already chose. And ID is equal to 1 milliamp per volt squared times 3 minus Vs minus 0.8 squared. So I just wrote the 2 equations I needed to solve for that drain current. Here's my Vs. Here's my VG. And so I'm just explicitly putting into the equation. Once again, we're still operating under a saturation. We can prove that. I'm just not going to bother at this point. But if we solve this, what we will get is that ID max is now equal to 1.13 volts, and VD is equal to 2.74 volts. And if we let VT equal to 1.2 volts, I can take the same equations, plug in the different VT value, and we will get that ID min will be equal to 0.87 milliamps. And VD is now equal to 3.26 volts. Okay. Compare those numbers to those numbers. What do we find happens to the bias point? It doesn't move around as much. What does adding RS do to the circuit? Adding RS stabilizes the bias point. And in fact, the larger RS, the less the bias point will shift due to delta VT. That's why we include that source to generation resistor in these circuits. It gives us a more stable bias point. We can pull different transistors out of the box and we're not going to see the current going all over the place. It stays within a certain variation, a certain tolerance. If we make it big enough, we can keep that tolerance small enough to where we can stand it. Okay, congratulations, you just saved $1 million on this production line. You're going to get a little certificate and you'll get a 2% raise next year. Congratulations. All right. That's your job, guys. All right. Well, fortunately, it's 2% of a really good salary already, though, right? So it's not bad. It's not bad. Okay. So this is why we do it. Now, the drawback is we've already seen. Adding RS reduces the gain. So what is the solution? Bypass capacitor. So we add a bypass capacitor to bypass R sub S. So that solves our gain problem. We have a stable DC bias point, but our AC gain has been put back where it was. Now it's not totally a free thing because adding R sub S also changes the dynamic range that's possible for your amplifier, for example. So it's not a totally free thing you get away with. But you can certainly work around a lot of these tolerance problems with things like this. Now, of course, I haven't also thrown in, for example, the tolerance of the resistors, the tolerance of other transistor parameters in the circuit. So one of your last labs you're going to be doing this semester is you're going to do what's called a Monte Carlo analysis, where you're actually going to do LT spice and you're going to throw in the tolerances. And you're going to run the Monte Carlo and you're going to tell me, given all the tolerances, if we basically look at random variations for all the components, what is the range of gains? Or what are the range of bias points to get out of the circuit? So incidentally, as design engineers, guess what you're going to spend a great deal of time doing? Monte Carlo analysis. Because they will always tell you, look at the corners of the design. What do they mean by that? They mean look at the extreme operating points due to tolerance and voltage variations and everything else, and make sure over every possible operating condition and every possible tolerance you may encounter, the circuit keeps working. So that's what you spend a great deal of time doing. Just coming up with a circuit is easy. Making sure it works every single time, in every one of those products that's out there where people's lives depend upon your product working correctly, that's hard. That's why you get paid the big bucks. All right? Otherwise, people will just pull this stuff out of books and just write it down and pass it over. It doesn't work that way. You design circuits to make sure they don't fail. Not just that they work, you make sure they don't fail. So, always something good to toss in, all right? All right, so we still have a couple more minutes. There is another actually common biasing scheme that I want to show you guys besides this, this voltage divider here. Now incidentally, you can also do tricks where you have a plus and minus bipolar supply, and there's a biasing scheme where you can literally just effectively ground the base, okay? And you can bias it that way. But I'm not going to bother to show you that. It's in the textbook because realistically, nobody uses bipolar designs in much anymore in practical design. It's always going to be unipolar supplies. So this is kind of normally what you're going to see. But there is another biasing scheme, and I'll quickly draw it out for you guys. But I do advise you to read the book because the book goes into some more detail about different types of biasing schemes. I'm just showing you the most common. But there are several different schemes you can do. But there is one that you do find is used, and this is gate-drain resistor biasing. So in gate-drain resistor biasing, we connect a resistor between the drain and the gate, and then just feed our input source with a coupling capacitor and connect that directly to the gate. Notice there's no source resistor here at all. But it turns out this circuit works actually surprisingly well. Let's assume RG is large. And by large, I mean typically in mega ohms. And certainly it's going to be much, much greater than R sub D. So we're going to assume it's very big. But it turns out the fact that it's a very big resistance doesn't really have that bad of an effect. What's the current into the gate? 0. What's the current through RG? 0, yeah. So RG may be big, but the current is equal to 0. And so therefore, VD, the DC voltage at the drain, is equal to VG for our DC bias point. And so you can take this circuit and we can now throw some values in. So I'm going to assume here, let's see. I'm going to do an example. Let's let K prime N W over L be equal to 2 milliamps per volt squared. Let's let VT equal 1 volt. And let's let RG be big. Let's let RG be equal to 1 mega ohm. All right. So I'm going to, let's say I want to set ID equal 1 milliamp. So I want to do exactly what we did a minute ago. I want to set the drain current equal to a milliamp. One milliamp here is equal to 1 milliamp here because the gate current's equal to 0. But I also know that VD will be equal to VG, which is equal to VGS, because there's no source resistance. So next time we'll come back to the circuit, and let's solve this. And now let's see what happens if we vary the threshold voltage. It turns out this topology, as simple as it is very resistant to component tolerances in terms of threshold voltage. So see you next Tuesday.